Okay. So, welcome back. Hope you had a wonderful weekend. Couple of things. Firstly, 1C. 1C is a big exercise and there are some challenging graphing questions in there. I don't want us to get bogged down in the graphing and get worried about it, because when we're graphing we can generally just rely on our calculator a fair bit. Okay? So your first test you won't have your calculator for, but there's no graphing. It's just pure algebra, it's just calculus. But then you're going to have your calculator for every other test involving graphing and the exam. So don't worry about the graphing. The most important thing to take away from 1C is solving exponential equations and solving logarithmic equations. So what I mean by that, like here's a pretty basic one, but if you have 3 to the x equals 5, solving that using logarithms, okay? Or if you have ln of x take 1 equals 7, that's a logarithmic equation, solving that. So solving exponential equations, solving logarithmic equations, that's the core skill that you need to take away from 1C. Okay, so then today we're doing 1D. That's going to be a recap of the unit circle that you've done in year 11. So we're going to do we're doing basically a unit in a lesson. We're going to be summarising a lot of those things. So that's going to be today. On Wednesday we don't have our lesson in lesson 1 and 2 because we have the ducks assembly. Alright, and then on Friday I'm going to be away, but we're going through 2A on Friday. So it's already filmed from last year, it's a good quality video, and I've got the new booklets for chapter 2 and 3 ready to go. We'll hand them out and talk about them in a moment. So today 1D, Wednesday we'll miss a lesson, so you can just have a bit of catch up homework, and then 2A you can make your way through it when you've got time. So 1D, trig and the unit circle. So here we've got the unit circle, right? And I've given you a copy of it, and this copy I want you to keep, and if you want, you're allowed to bring this along to any of the tests that we have, okay? So you can bring it along rather than writing it on your cheat sheet and so forth. So just to go through the copy I've given you, this is a pretty comprehensive version because it's listed a number of things on there, right? So the first thing you'll notice as we go around the circle is the angles in radians in simplest form, okay? So pi on 6, pi on 4, pi on 3. Just next to that, moving out of the circle, we've got the angles in degrees, all right? And then on the outside, the coordinates, so the x coordinate, the y coordinate, so the cos value, the sine value, and then the one outside of that is the tan value. So it's giving you the tan value as well. We've got cos is x, y is sine, and tan is sine divided by cos. So that's the last value on the outside. Other than that, we've got the ASTC, so I like to say all students talk cool, and what that means is all ratios are positive in this quadrant, sine is positive in this quadrant, tan is positive in this quadrant, and cos is positive in the last quadrant. Okay, so in the first quadrant, all of them are positive. Here, only sine is positive, which means both tan and cos are negative. So there's a review of the unit circle for you. If you want to know how we generate it and so forth, I'm happy to go through that, but that's sort of more year 11 content. Let's just get straight into the application of it. So we can read through the dot points that I've summarised there. I think the two main properties that you need to remember is firstly sine squared theta plus cos squared theta is 1. Okay, so that's the Pythagorean identity. And then the other one is tan theta is defined as sine divided by cos. Alright, so there are two identities that we need to remember going forward. Then we've got a description of how we calculate angles. Okay, so we can use radians or we can use degrees. Radians is a measure of radii of the circle around the outside of the circle, and degrees is an arbitrary number where we split a circle up into 360 equal parts. I used the example of cutting a pizza into 360 pieces. So that's the theory. Let's do the maths. So we've got find cos theta, sine theta, and tan theta. Given theta is 7 pi on 6. Okay, so 7 pi on 6. That's an angle. It's an angle in radians. And what we're doing is we're going to look at our unit circle. We're going to locate that. And we're going to find what's the value of sine of theta, given theta is 7 pi on 6. What's the value of cos of theta, and what's the value of tan. So we can look straight at our unit circle. Sine is the y value, okay? X is cos, sine is y. So at 7 pi on 6, the y value is minus half. All right. The cos value is negative root 3 on 2. And the tan value is provided for us there, but I want to show you how we can calculate that as well. So this is question 1, right? If tan is sine divided by cos, and we wanted to know tan of 7 pi on 6, then it's going to be sine of 7 pi on 6 divided by cos of 7 pi on 6. Okay, we've identified both of those already. That's going to be negative half divided by negative root 3 on 2. So there's a reason I want to do this, is it allows us to go over some of these fraction operations again. Now, in this fraction, we've got a negative at the top and a negative at the bottom, which means when we perform it, it's going to be positive. Okay, a negative divided by a negative is going to be a positive number. That's also confirmed because our angle is in the third quadrant, right? It's 7 pi and 6, where only tan is positive. So it's confirmed, right? So the negatives can cancel. And we have half divided by root 3 on 2. I like to just follow this as a rule of fraction division. If we have A on B divided by C on D, it's A times D divided by B times C. That's what it simplifies to. We learned those fraction skills in year 8, by the way. Not that I expect you to remember them, it's a long time ago. So that's what it's going to simplify to. So if we go here, A corresponds with 1, B corresponds with 2, etc. So we're going to do AD on BC. So we're going to have 1 times 2 on top of 2 times root 3. We've got 2 at the top, 2 at the bottom as a product, so I can cancel, and we're left with 1 on root 3. Again, it's confirmed in this unit circle. I've given you the tan values. Okay, the tan values being the ones on the outside. All right, so that's the first question. Any issues so far? Very good. So let's move on to question 2 then, where we have find the value of theta given cos of theta equals root 3 on 2, and we're given a constraint. 0 is less than theta is less than 2 pi, which means we're only considering one revolution of the unit circle. So we're going to look at the unit circle and we're saying, when is the x value? Because cos of theta is the x value, right? When is the x value equal to root 3 on 2? So here's how we should think about it, is root 3 on 2 is a positive number. All right, you can evaluate in your calculator, it's about 0.866. So if we're saying the x value, this is the x-axis, the x value, when it's positive 0.866, it's going to correspond with these points. All right, so you can localize it just by understanding what is it asking you. It's a positive value of root 3 on 2. X is positive. So we're going to be looking here and here roughly. So you're looking there for where the x value is root 3 on 2. And you can see it corresponds with pi on 6 and 11 pi on 6. Okay? They are the two solutions. All right? In both of those points on the unit circle, the x value is root 3 on 2. Now, how come I answered in radians? Well, I answered in radians because the question restricted the domain in radians. So it sort of dictated the method in which it wants me to answer, because it's giving me that piece of information there. All right, it's given me the question in radians, I'm going to answer it in radians. Okay, so we'll move on to B. We have 2 sine theta equals 1. Okay, so for this one, we need to first isolate sine theta by itself. We've got this 2 out the front, 2 times sine theta. We're going to divide both sides by 2. All right, that's going to give us sine theta is half. And then we're looking on the unit circle. Where is the y value? Okay, now we're talking about the y value. Where is the y value? Positive half. Okay, so we're going to be looking here and here. We can localize the points that make that true. So on the unit circle, when is sine theta half? Sine is the y value. We've got pi on 6 and 5 pi on 6. Okay, now that's within one revolution, right? For the last one, we might pretend that there is no restriction on the domain. Alright, so both of these questions say, find this given this restriction, okay? Find this given this restriction. Now with question C, we're going to say, find this, sine squared theta equals 0, given no restrictions. There are no restrictions on the domain, alright? Find all solutions, all values of theta that make it true. So, same thing applies. We need to get sine theta all by itself. So we'll take away 3 from both sides first. We divide both sides by -4. We will square root both sides. Now when we square root, the answer is plus or minus, isn't it? It's going to be plus or minus root of 3 on 4. Because we could have the negative solution or the positive solution. Now we're going to simplify that using surds. Alright, so those surd operations there, assumed knowledge, we learned them in the second semester of year 11. Okay, splitting the denominator, applying the root to both the top and the bottom, and then square root of 4 simplifies to 2. So we've broken this down, and the solutions to this equation are the values when the y on the unit circle is equal to positive or negative root 3 on 2. So again, think of your unit circle, here it is, and we're going, when is the y value is here, positive root 3 on 2 or negative root 3 on 2. Okay, so they're going to be the negative solutions, here's going to be the positive solutions. Here we have positive y, above 0. Here we have negative y. And so let's find them on our unit circle. When is y positive root 3 on 2? We've got pi on 3. We've got 2 pi on 3. That's when it's positive. When is it negative? We'll have 4 pi on 3 and 5 pi on 3. Now, those would be the solutions within one revolution of the unit circle. Alright, they're the solutions within one revolution. But I've said here, let's not restrict the domain. Let's find all possible solutions. So when we're asked to find all solutions, what we need to say is, these are going to keep reoccurring, because if you keep going around the unit circle, they're in the same position. Alright, look at the first one, it's here. And then if we go the whole way around, we've travelled around, how far is it the whole way around? 2 pi, okay? So it's going to be this one again, plus 2 pi, this one again, plus 2 pi, this one again, plus 2 pi, and you can keep going around as many times as you want. So anyway, the way we notate that we've got every possible solution is we say plus or minus k2 pi. Alright, we can just keep going around, multiples of 2 pi, for all k is an integer. Alright, so I'll break down what that means exactly. So this is mathematical notation, alright? Plus or minus k times 2 pi. So plus or minus multiples of 2 pi, provided for all, that's what that symbol means, for all k some values. E means belongs to, and z is the set of integers. And what are integers? Integers are whole numbers. So that's what that notation means, okay? But the important takeaway from it is, if we want to include all solutions for a trig equation, that's how we're going to do it. Plus or minus k2 pi for all k e z. Alright? So it looks cool. Splendid. Okay, so let's move on to the next one then, which is find cos and tan given sine of theta is 3 on 5. So sine is the y value, and if you're looking on your unit circle, sine is the y value, and it is 3 on 5. And if you're looking on the unit circle, you won't find 3 on 5 anywhere. Okay, that's not one of the multiples we have for an angle here. So we're going to have to use a different procedure. Now there's two ways we can do this. Again, I'm going to show you both ways. So we want to find cos, and we want to find tan. So the first one is that this is true. Sine squared theta plus cos squared theta equals 1. We know that sine is 3 on 5, so we can substitute that in there and solve for cos. Alright? And we do have a restriction of the domain. Someone's calling me. Pi and 2 less than theta less than pi. So let's do that. This is the method we're going to use first. This is using the Pythagorean identity. We're subbing 3 on 5 in here. So we're going to have 3 on 5 squared plus cos squared equals 1. And we're breaking it down, get cos theta by itself. We'll have 9 on 25. We'll subtract 9 on 25 from both sides. Okay, again, for the fraction operation, 1 take away 9 on 25, we need them to have the same denominator. So I'm going to do these nice and manually. Alright, when you've got your calculator, you can use it. So 9 on 25. 1 we express as 25 divided by 25. So we'll get 16 on 25, and then when we square root it, we'll get plus or minus 4 on 5. Okay, but there's one more step because we have a restricted domain. Alright, we have a restricted domain which is from pi on 2 to pi. So on our unit circle, from pi on 2 to pi, that is this region. And in this region, only sine is positive. We can see x values are negative. They're left of 0, right? X values are negative, which means cos is an x value, and so our solution must be negative. So therefore, we're going to write it like this. Cos of theta is negative 4 on 5, as positive 4 on 5 is rejected because of the region. Rejected means it's not one of the solutions to our problem because it's outside of the constraints that we are given. Okay, so we found cos, because that's the way we did it, using the Pythagorean identity. Okay, there it is there, we found cos. Now to find tan, we could use the tangent identity. That tan, I haven't got it written up anymore, but tan is sine divided by cos. We've got a sine value, we've got a cos value, so we can find tan that way. Okay, so that was the first procedure. The other procedure I want to show you is using right angle trigonometry. Okay, so we've got sine is 3 on 5. Now I want you to remember back to year 9, all right, where we have SOHCAHTOA, right? SOHCAHTOA. So we have sine is equal to O on H. O on H. And here we've got sine is 3 on top of 5. So we can draw any triangle, right? Any right angle triangle. Where this is our angle, here's the right angle. If I'm going to label it, this is my hypotenuse, this is my adjacent side, this is my opposite side. Now we have sine is 3 divided by 5, is O on H. So O corresponds with 3, and H corresponds with 5. Right, we have 3 there, and we have 5 there. Okay, this is a good process for us to do because it allows us to recap some Python. Now, we want to know what is this adjacent side, right? Cos is A on H, so that means we need A if we want to determine the cos value. So, if we think of Pythag, we're going to have A squared plus B squared equals C squared. As a statement, A squared plus 3 squared equals 5 squared. Alright, here's A, here's B, C is the hypotenuse. And we can go through and solve this for A. A squared plus 9 is 25. A squared equals 16. A equals plus or minus 4. So we've got A is plus or minus 4. cos is a divided by h. So therefore cos is plus or minus 4 divided by 5. Okay, just like what we had here, plus or minus 4 and 5, and then we can localise the solution given the constraints, given the domain. Okay, so two possible ways there that you can generate the answer. You can use the Pythagorean identity, or you can draw a right angle triangle and use Pythagorean, just sort of use a bit of intuition. I need to answer the tan part anyway. So tan is sine divided by cos. So it's going to be 3 on 5 on 4 on 5. Right, sine divided by cos. So what's that going to be? We're going to have 15 on 20, we'll get 3 on 4. And one of them is negative, cos is negative, so that one's negative, so our answer is negative. All right, we have a positive divided by a negative, so our answer is negative. Another way that we can confirm this is true, we determined A is 4, tan is O divided by A, right? Tan, TOA, O divided by A, 3 divided by 4, okay? So we're getting more confirmation all around the place. It all links up together as an enclosed unit. Okay, so can I just see, show of hands, who's done this process before, the Pythagorean identity? That should be probably what we did last year, yeah? Who's done this process before? Yeah, a couple is, excellent, all right, so we're seeing a bit of both. Wonderful. All right, let's move on then. So we're going to turn the page now. So there we were talking specifically about solving trig equations. What we're going to do now is look at trigonometric functions. So we're looking at the graphs of them as such. And this is a really good place for me to demonstrate general translations, dilations, reflections, etc. of functions. So I'm going to be using Desmos a bit. We have the basic sine and cos function illustrated here. So we've got here the first point, these functions are periodic, that means they repeat themselves forever in the horizontal direction, they keep going forever. And we have the base function, a sine b of x take c plus d. Now I want you to compare that with, this goes for any function, a times f of b of x take c plus d. Alright? So if we have some function f of x, a, b, c and d, they're all the ways we can manipulate it. And you guys did that in your roller coaster folio. That's one of the crowd favourites in terms of maths folios. Alright, so manipulating the different functions by changing these values of a, b, c and d. You'll be doing the same this year with the folio you get as well. So pays to be competent at it, and Desmos helps us out here. So you can see here we're talking about the transformations from sine of x to here, and here we're talking about the transformations from f of x to here. So they all affect it, right? A is the amplitude, B is how many wavelengths occur in 2 pi, C is the horizontal translation, D is vertical translation, period is 2 pi divided by B. Okay, so let's get into the questions we've got then. So we've got a table here where we've got amplitude and we've got period. Alright, and we've got a couple of functions. We've got 2 sine of x, we've got a third sine of 4x, we've got 0.5 cos of pi on 3x. So, and we're asked what's the amplitude and what's the period for these functions. So the amplitude is just the number out the front, right? 2, so it's doubling the function, okay? Because we're multiplying every sine of x value by 2. We're doubling it, and so it's going to stretch it further away from the principal axes. A third, it's going to be a third, okay? We're multiplying every sine of 4x value by a third, and then the last one, half. 0.5 is equal to half, okay? So that's a conversion that we will use a bit. Then we've got period. Period is how far is it for one wavelength. What is a wavelength? That's the duration, the magnitude, the size of how far is it for one whole peak and one whole trough. Another way you can measure it is it's the distance from peak to peak, all right, or from trough to trough. That is one whole wavelength, the distance for a whole peak and a whole trough. And the wavelength is equal to 2 pi divided by b. What is b? b is the coefficient of x. It's always the number in front of x. So here, the number in front of x is 1. We've got the invisible 1. So our period is 2 pi on top of 1, which is just 2 pi. Which means for our first sine wave, for one whole peak and one whole trough, that distance there is 2 pi. Alright. For the next one, we have b is 4. So our period is going to be 2 pi divided by 4. That simplifies to pi on 2. Okay? So what that means is for one whole wavelength for this function, it's only pi on 2 units. Remember, pi is just a number. Pi is 3.14159. Pi is just a number, and so that is a distance for us. Half sine 4x. Now, the other thing I want to say about the value of b is b tells you how many wavelengths there are in 2 pi. Okay? So here we have a value of b of 1. There is one wavelength in 2 pi. Here we have a value of 4, which means there are 4 wavelengths of this function in 2 pi. If we were to draw this function and this function on the same axes, the second one's going to have like 4 wavelengths. They're compressed in together. Okay, the value of b, how many wavelengths are there from 0 to 2 pi? All right, last one, 2 pi divided by pi on 3. Now, we have 2 pi divided by, in this case, pi on 3 is its own number. It's some number, right? And so here's how I would think it. We've got 2 pi on top of 1 at the top. That's the number at the top. What's the number at the bottom? Pi on 3. Okay? And then we can do our AD on BC. 2 pi times 3 is going to be 6 pi. 6 pi on pi, and it simplifies to 6. All right? The distance for one whole wavelength is 6 units. That's our period for this one. All right? So, I said 2 pi is our number at the top. We express that as 2 pi on top of 1. All right? That's our first number, divided by our second number, AD on BC fractions. Okay, then we're going to be finding the equation of some of these trigonometric functions. So bear with me while I sketch them up, because I will point at them as we do it. So, we've got from 6 to 2, we have peak, drop, peak is 2 pi, and here's 4 pi. And we need to determine A, B, C, and D, and whether it is a sine or a cos function. Okay. Now, sine and cos, you can say that they are the same function. It's just one's a horizontal translation of another. That is true. For our purposes here, though, we should try and say what starts at a peak. Okay. So the cos function starts at a peak, and the sine function starts at the middle there. Okay. So that's the sine function, and that's the basic cos function. So when we're looking here, it's got a peak at 0, so that means we're going to be using cos to start with. Now, the first thing I like to look for is the principal axis. That is the line about which the function propagates itself. And that's going to be exactly halfway between the peak and the trough. Okay, we can draw a dotted line there to represent that. That's what we call the principal axis, and that is always the value of d. That's always the vertical translation. All right, if there's no vertical translation, the principal axis is the x-axis. Here we can see it's been shoved up a bit. We've got some plus something. We've done all the calculations, and then we've got plus some number. And that number is exactly halfway between 2 and 6. It's going to be 4. Okay? Our value of d is 4. That's our vertical translation. The equation of the principal axis is y equals 4. Okay, then our amplitude is just, well, how far is it from the principal axis to a peak or from the principal axis to a trough? What is that distance? Our amplitude is 2. And b, there's a couple of ways we can determine b. I think this is the clearest way to think about it. Remember over here, b, that number tells you how many wavelengths are there in 2 pi. How many wavelengths are there in 2 pi? Well, over here, we can see we have one wavelength in 4 pi. All right, which means we have half a wavelength in 2 pi. So our value of B is half. There is half a wavelength in 2 pi. All right, so that's the quickest way to do it. When we get to the next one, the next one's going to be pretty similar as well. Here's how many wavelengths there. Okay, so that's the first one. C, there's no horizontal translation, and if you're asked to find the equation of the graph, there won't be any horizontal translation, okay, because that can mix up on the x-axis, it can look a little bit confusing. So we will leave C out for now, but all that's going to do is shove it left or right. Alright, so let's move on to the next one. So we got here from now we've got I'm only going to sketch it to there. I won't sketch the whole thing. So we have 1, okay, 1.5. So we go there. Alright, x, y, this point here is -1, -3, -5. Cool. Alright, so we need to find the values of A, B, C, and D. B, C, D. Now this one, we're looking at the shape of it, okay, it's starting at the middle, so we'd say it's going to be a sine function. Here's the principal axis, alright, that's the line about which the function propagates itself. It's going that way forever, it's going that way forever, about the line y equals -3. The vertical translation is -3. No horizontal translation. Our amplitude is always going to be a positive number, okay, unless it's inverted. So, but amplitude we generally say is the magnitude of from the peak to the principal axis or from the trough. So A is going to be +2, and then B. B is how many wavelengths are there in 2 pi? Another way, yeah, no, it's not going to work with this one. I'm just trying to think. I need a good example to show the other procedure. But here we've got, well, you can see we've got one half a wavelength. Here's another half a wavelength, and here's another half. We've got 1.5 wavelengths. So our value of B is 1.5, or as a fraction 3/2. So let's answer these questions. It said find the function. Well, here it's going to be 2 cos of half x plus 4. Alright, so we decided that one was cos, and then I'm just putting in A, B, and D. And then the same over here, y equals 2 sine of 3/2x, take 3. Okay, you sketch that in your calculator, that's what it's going to produce for you. Alright, so there's a pretty, what we're doing there, guys, is a pretty thorough recap of a whole unit that you cover in year 11. So hopefully it's not too overwhelming. You will find the questions in the book, there's only 5 of them, and you will find them probably a little bit easier than some of the things that we have been doing up here. So, are there any immediate questions about what we've been going over here? Wonderful, so let's get into 1D. I'm going to float around, see how we're all doing with everything. So I'll chat to you shortly. Should be true.